Hello viewers, welcome back to the part 3, the final part of our lecture, Variational Formulations in Finite Element Method. In part 1 and part 2, we built the foundation with weak formulation and energy principles, and we derived the weak form of one-dimensional bar. Now in part 3, we will see how to actually solve this problem using Galerkin's method, the heart of the finite element method. We also see how everything extends to real world 2D and 3D problems. This is where the theory becomes computation. Galerkin's method. It is the heart of the finite element method. This is where we transform our continuous mathematical problem into a discrete system that computers can solve. The fundamental challenge, right? The fundamental challenge of this thing is here, because we cannot find exact solutions for most practical engineering problems. The exact displacement function u of x is unknown and impossible to determine analytically for complex geometries. We approximate the solution using simpler functions and that we can work with. The trial function approximation. We approximate our unknown solution, that is u of x, as a weighted sum of known basis functions. U of x equals u of x bar, that is summation of I is equal to 1 to n, that is ni of x into di. So here if you see, the ni of x is the basis function or shape function. So ni of x is nothing but the basis or the shape function, right? So here if you see, we use linear polynomials, quadratic polynomials and cubic polynomials. These are called shape function in finite element terminology because they define the shape of the solution within each element. The key property ni x of j equals sigma of ij. Here the Galerkin's key choice uses the analytical function spaces for both the test and the trial function, right? So this symmetry distinguishes Galerkin's method from classical Ritz approach. And the next part is the system generation. If you see here, that is a k into d is equal to f. This is the transforming calculus into linear algebra. So in this slide you can see the assembly process, right? The assembly is the step-by-step process, right? First what we have to do is the first thing is some element contribution, which means we have to find the solutions according to the problem, right? So the solutions are found out for each element. So each element, for example, element 1 we have to find all the stiffness values, etc, etc. Similarly for element or element n, right? So we will find individually for all the elements, then finally we will sum up all the elements. So this forms the first step of the assembly process, right? And the next thing is the boundary conditions, right? Natural boundary conditions. So here the natural boundary conditions such as self weight or one and what the fixed things, right? So are all determined here. Then the next step is about the essential boundary condition. So here if you see, that is the modifying the K system, which means the stiffness matters. If you see, when you apply the boundary condition, for example, one end of the element is fixed, then what we'll do is we will neglect the particular rows and columns according to the matrix, right? Then we finally form an equation that we solve for the unknown nodal displacement. That is the step number 4. Finally we will find the stresses of the elements, right? Nodal points, right? Stresses at each nodes of the elements are found out. That forms the post processing, or the step number 5 of the assembly process. So you can see the extension between the 2D to 3D elasticity. So here, if you see this variational framework naturally extends multidimensional continua, which maintains the same fundamental structure while accommodating the tensor and additional geometry complexity. So if you see the weak form, that is the 2D or 3D, generally, here the sigma ij is the stress tensor. This sigma ij is the stress tensor, and this value, that is a sigma of epsilon ij, is nothing but this epsilon ij is the strain tensor, right? And bi nothing, it is nothing but it is the body forces, right? It represents the body forces, and ti denotes the surface traction. So this is what the formula or the generalized form for the multi-dimensional elasticity, right? And if you see the things, what we can say, the structure is identical to 1D, that is internal virtual work equals to external virtual work. For linear elasticity, here you can see here, for linear elasticity, this D is nothing but it indicates the relation between the stress to strain, right? This stress to strain. And if you see here, the B denotes the strain displacement matrix, right? And the physical meaning is K is equal to B transpose dB, which means it quantifies how nodal displacements produce forces through material deformation. And next you can see here about the global assembly solution, and here the global assembly is identical procedure to one dimension. So global K, that is global stiffness K, is equal to summation of over all elements, right? So each element contributes global matrix contributions or global matrix positions corresponding to its nodal numbers. So finally, the solution, that is nothing but solving K into D is equal to F. So D contains the displacement for each node. So here if you see, the variation framework is dimension independent. So 1D bar, 2D plane stress or strain, the same formulation. 3D is solid mechanics, the same formulation. Even it extends to plates, shells or beams. Only the matrix size and the elements type can change. The fundamental mathematics remains the same. So next we are going to see about the properties of the variational formulation. So here you can see there are different properties according to which the major properties are, you can see the first one is about the equivalence. So the equivalence here represents the weak and strong forms are mathematically equivalent. And the second property is the reduced continuity requirements, which means the strong form demands, then the weak form requires everything, right? So this relaxation permits piecewise polynomial approximations. And the third property is about the natural boundary conditions that emerge automatically. So here natural boundary conditions appear originally during integration by pods, requiring no explicit enforcement. And property number 4 is nothing but the symmetry of symmetry for self-adjoint problems. When the bilinear form satisfies, the resulting K matrix is symmetric. For elasticity, heat conduction and many other problems, we get symmetric matrices only. And the next property is the optimal approximation. So the Galerkin approximation, U minimizes the error in energy norm along all functions in the approximate space. This is the best fit property where we are getting the best possible answer within our chosen function space. The last property is nothing but the guaranteed convergence. As we refine the mesh or increase the polynomial order, the approximate solution converges to the exact solution. So let us see the mind map finally. So you can see the strong versus weak form and the variations in FEM, right? So here if you see the strong and weak form, you can see the differential is strong, the integral is weak, right? And the variation formulation in FEM, that is a weak derivation of one-dimensional bar. So multiplying the test function, so integrating the parts and natural boundary conditions that appear. So the virtual work principle, that is internal work versus external work, and minimum potential energy, that is dou pi is equal to 0. And Galericon and discretization. So here the trial function, test function and the stiffness that is discussed. Finally the properties and significance, that is symmetric stiffnesses, automatic natural boundary conditions and energy approximation. So that's it about the lecture, and we will meet in the next lecture series. Thank you.